my channel.
So last class we have discussed about the first row of transition metals. So for this week we are going to learn about what we call coordination compound. So what do you understand about coordination compounds? Have you ever heard about coordination compounds? This part 1, we will be talking about coordination compounds and also the types of complex ions. So for the first one, what do you understand about coordination compounds? It is actually a species in which a central metal ion or atom is attached to a group of surrounding molecules or ions by coordinate covalent bonds. So let's say I have here, this is where we have the metal ion or atom surrounded by what we call molecules or ions. Okay, this is molecules or ion by coordinate covalent bonds. This is not a common bond. This is what we call coordinate covalent bonds, where the molecules or ion here are sharing their 2 electrons to the metal. So this is where we have the molecules or ions that we call ligands, or the definition for the ligands are surrounding groups. Okay, surrounding groups for the metal here. And then other than that, you need to know what is Lewis acid, what is Lewis base. In this case, this Lewis acid is actually the central metal. This is the Lewis acid, and the ligand will act as Lewis base. The Lewis base here. Other than that, in coordination compound, you need to know what is the coordination number, or we call it as CN. This is where the number of ligand donor atoms. For this case, for example here, this is example here, the coordination number, the CN for this metal is 4. Why? Because we have 4 ligand here. 1, 2, 3 and also 4. Other than that, the coordination compound is usually consists of a complex ion and a counter ion. And this complex ion is actually contains a central metal cation bonded to one or more molecules or ion. This is where we call them as ligands. The ligands here. Okay, right? So the ligands, in order to become a ligand, it must have at least one unshared pair of valence electron, because these ligands act as a Lewis base. Other than that, okay, the counter ion is actually a complex ion associated with other ions. For example, the water, H2O here, ammonia, NH3, the carbonyl, the CO, and also the chloride here. Because why? As you can see, the H2O, the ammonia, the CO here, and also the chloride, they have minimum at least, okay, one unshared pair of valence electrons. As you can see from here, H2O we have two pairs of valence electron. Ammonia we have one. The carbonyl, the CO, we have two, one at oxygen and one at the carbon, and chloride. So for this example, okay, this is a cobalt compound. We have two kinds of ligands, okay. because we have chloride here and we have ammonia here. In coordination compound, ammonia, this is what we call amine. A-M-M-I-N-N-E, amine. Next this is the counter ion. What do you understand about counter ion? It is actually an ion that having a charge opposite, okay, a charge opposite to that of the substance with which it is associated. From this example, you will see this is where you have the ligand, the amine here. We have 6 amine. And then other than that, this is what we call complex ion because it is a combination of complex, and this complex has a charge, okay, ion, positive 3 here, right? So because we have complex ion with a charge positive 3, so we need to have 3 counter ion. For example, here we have a chloride, okay, that actually will give you negative 3 in order to neutralize this positive 3. So overall, this complex ion and combination of counter ion, it will produce what we call coordination compound. So in this slide, okay, first thing is you need to be able to differentiate which one is the ligand, which one is the complex ion, and which one is the counter ion. So here we have also cobalt, hexaamine cobalt 3 in the presence of a 3 chloride ion as counter ion. So here, what is coordination complex? So the things that you need to have for a coordination complex, first is you need to have ligands, molecule or ion surrounding the metal ion. Second one, you need to have metal ion as a metal center. Third one, you need to check the charge on complex, whether it is actually neutral or charged. Last but not least, you need to have counter ion. So for a coordination complex, you need to have 4 things here. You need to have metal ion as a metal center. You need to have ligands, whether they are molecules or ions surrounding the metal. Third one, you need to check on the charge on complex, whether it is actually charged or neutral. And last but not least, you need to check the presence of counter ion. Okay, in order to differentiate which one is a ligand, which one is the counter ion, anything in the bracket here will be the metal ion and also ligands. Outside the bracket here, this is where we have the counter ion. So the central metal ion here in purple center is actually surrounded by a set of ligands in the blue one here. And the ligand actually donates 2 or more electrons because they have lone pair to the d orbitals, because we are dealing with the transition metals around the metal and forming a dative or coordinate bond. So the dative bond here, usually we write it down as an arrow. Okay, in an arrow in order to form or in order to show that this is a dative or coordinate bond. So a complex ion actually consists of central metal cation, and then usually derived from the transition metal, joined by coordinate covalent bonds to 2 or more molecules or anions called ligands. So in order for you to have metal complex, you need to have a metal center and also ligands. For example, here I have 3 examples. For example, we have a silver. For the first one, we have silver with amine. So this is the metal and this is the ligand. Okay. The cation is the silver one. The ligand here is ammonia, or we call it as amine. So how many ligands do we have? We have 2 here. And what is the coordination number? Means here number of bonds formed between metal and also ligands. So because we have 2 ligands, so we have 2 coordination number. Other than that, second one, I have a copper here. We have water, H2O, as ligands. So how many water do we have here? We have 4. So this is actually a tetra aqua copper 2. So the cation is copper 2 plus. And the ligands here is a 4 H2O or 4 water molecules, or we call it as aqua. So I will be teaching you guys how to give nomenclature on coordination compounds in part 3. And then, okay, what is the coordination number? Because we have 4 water, so we will have 4 coordination number for this complex. Third one, we have iron. So this is CN, cyanide. So in order for you to give the name for cyanide, it will become cyano. So here is the 6. So because we have 6 cyanide, so it will become hexacyanoferrate. Okay, hexacyanoferrate 3. Okay, why this one as a ferrate? I will explain to you guys in part 3. And the cation here is iron 3. And we have 6 cyanide ions. So the coordination number here is 6. With 6 cyanide ions. Okay, for example, let's say, okay, let me draw one example here. Okay. First one, this is the silver. And then this silver is actually connected to 2 ammonia, NH3. NH3. So for this one, how to determine the coordination number? Because we have 2 bonds here. This is 1 and this is 2. So the coordination number is 2. It's actually, you need to determine how many bonds form between metal and also ligands. So we have 2 here, so the coordination number is 2. Other than that, let's say we have copper. Okay, we have copper with 4 water, 4 H2O. This is the O, and then H2. This is another O, and also O. So the bonds that actually form between copper and also oxygen is 4. So the coordination number is 4. The same goes to this example number 3, because we have iron 3 here. Iron 3 here with 6 bonds. Or with 6 cyanide surrounding the iron, this iron. So this one will give you coordination number of 6. So this is about what we call complex ion. Okay, so as I mentioned before, you need to understand what is the definition of coordination number. It's actually number of ligand atom bonded directly to central metal ion, and then this coordination number will also give you will give metal ion in a particular oxidation state and also compound. Other than that, you need to determine, or you need to understand what is the geometry. This is actually a shape of the complex ion, depends on the coordination number, and nature of the metal ion. And then also we have ligands. Okay, it is actually a molecule or an ion with one or more donor atoms. So first thing, the most important thing for a ligand, it must have one lone pair, minimum one lone pair. And then ligands also actually can donate this lone pair to metal ion in order to form what we call dative covalent bond. So please add on word of dative here. Dative covalent bond. So for example, let's say I have this iron 3 with 6 water molecule. So this is actually hexa aqua ferrate 3. Okay, hexa aqua ferrate 3. So what is the geometry for this hexa aqua ferrate 3? Okay, so the geometry for this one, as you can see, we have 6 coordination number, right? So this one will give you an octahedral geometry because we have 6 bond here. Okay, this is what we have discussed or we have learned before this in hybridization and also VSEPR. Okay, and then another examples here, I have titanium. We have here tetrachlorotitanium 1, and then this titanium is dissolved in water, H2O, and what happened here, it will produce titanium oxide, okay, and also hydrogen tetrachloride. So it is actually a coordination compound that can work as semiconductor, okay, or this is a network solid of titanium oxide. This is what we have learned during our class for metallic bond, right? Semiconductor. So you have the small gap between the valence band and also conduction band, right? And then what is the coordination number for this titanium? TiCl4, tetrachlorotitanium 1. It is actually dissolved in water in order to form titanium oxide. This is a solid, and also hydrogen tetrachloride. Do you still remember about semiconductor? This is what we have learned during our metallic bond, where we have a small gap between the valence band and also conductance band, okay? And then other than that, this TiCl4 or tetrachlorotitanium 1 has 4 coordination number because we have 4 ligands here. And then the ligand here is a chloride. Okay, and the charge here is neutral. Why? Because we have a positive for titanium with a negative for chloride, because we have 4 chlorides here. 4 times negative 1. So the total charge for this compound is actually 0, a neutral. Then other than that, we have a cobalt here. Cobalt complex, okay, ion. Because why? Because we have positive 1 here with the coordination of 6, because we have 6 ligands surrounding this cobalt, and then we have 6 bonds, okay, surrounding this cobalt 3. And the types of ligand here, we have chloride and also ammonia. And the charge, overall charge for this complex ion is actually positive 1. And then with the cobalt is positive 3. And the chloride here is 2 times negative 1. So here you get positive 1. Okay. So in this case, in order to neutralize this positive charge, we need to have at least one counter ion that give you a negative charge of negative 1 in order for you to neutralize this compound. So what happened here, this complex is charged, and so must have at least one counter ion. For example, this is where we have the cobalt with 4 ammonia and 2 chloride with the presence of 1 -1 here. This is the counter ion. Okay, so anything in the bracket here must contain metal and also ligand. Okay, one metal and ligands. So other than that, other than outside from this bracket, this is what we call counter ion. Okay, so what happened here, this complex actually will ionize in solution. When they ionize in solution, we can call it as electrolyte. So this compound can act as electrolyte. So it can actually conduct electricity in liquid form. So other than that, here we have geometries. Okay, so if you have two ligand connecting to one metal, this is what we call linear. For example, here we have copper 2 chloride, and then we have here 4 coordination number. So this is the coordination number of 2. This is where we have the coordination number of 4. Why? Because we have 4 bonds surrounding the metal. And then we also have the coordination number of 4 here. Because this metal also has 4 ligands surrounding metal and 4 bonds surrounding metal. But as you can see from here and here, okay, they have different geometries. This one will have the tetrahedral geometry, while this one will have square planar geometry. Why? This one I will explain to you in, I think, in what we call CFSE. Okay, CFSE in crystal field splitting energy later on the next class. Okay, so how to differentiate between tetrahedral and square planar. And then other than that, I have one example for octahedral, because why? Surrounding the metal here, we have 6 bonds. 1, 2, 3, 4, 5, and also 6 bonds. So this is where we have the coordination number of 6 for titanium and also chromium. And last but not least for this part is, this is where I have 2 exercise for you guys. So for these 2, cobalt and also silver one, okay, you need to determine the coordination number, what type of ligands, and also what is the geometry for these 2 complexes. So guys, I think that's all for this part. So hope to see you guys in part 2 soon. Bye!